Alright, after talking about the advantages of data augmentation, let's actually try out these data augmentations in practice using Torch Vision. So in this notebook, since we are not training the model itself, we are not using a PyTorch model, we are just looking at the augmentations that we are going to apply in the next videos. It's always a good idea to test out the augmentations before we actually apply them to the model, because sometimes we can, by accident, come up with augmentations that are not realistic and that then distort the images such that we get poor performance. So let's take a look at the augmentations here. So we are loading, of course, first our imports, and then we are going to use the same Cypher10 data module that we used in the previous notebooks. So it's our Cypher10 data module that we import from our local shared utilities file. Yeah, and then as usual, I also like to take a look at the images just to make sure that they load properly and also to get an idea of what I'm working with here. And now comes the interesting part, the data transformations. So we are going to tackle this step by step. So first I will show you a few of these transformations and explain what they do. And then later on, we will take a look at how they affect the images. And then of course, in the next videos, we will also apply them to the residual networks. So here we are importing transforms from Torch Vision, and then we are building our image composition here. So this is essentially a pipeline kind of like analogous to Torch sequential when we are building our neural networks, where we are connecting multiple layers, but here we are connecting multiple image transformations. So they are executed one after the other. So first, we start with converting the image from PNG or JPEG into a Python imaging library format. So PIL stands for Python Imaging Library, and this is a specific file format here that is produced by this call. And then in this file format, we apply different transformation. And then after these transformations, we convert the converted image or the transformed image into a PyTorch tensor, and then we normalize the tensor. So what are the different image transformations that we are doing here? So first of all, there is resize. So we are resizing our image from 32 by 32 to 150 to 150. So Cypher10 is, unfortunately, relatively small. So it's a 32 by 32 image that data set. And this is very, very, very small by today's standards. The only nice thing about that is it's very easy to download, and it's a pretty resource friendly because it's so small. However, most modern convolutional networks, they expect larger image inputs. So what we are doing here is we are resizing that to a, let's say, more proper form, at least 150 times 150, which is also not large, but it is at least, I would say, a little bit more, contemporary. So now after the resizing, we are then doing a random crop. So this means that from that original image, we are taking a smaller crop that is a subset of that image. And by that, we are essentially creating variations of the image. So if we have a given image and we take different random crops, each of the random crops will be slightly different, and that can help the network with a generalization performance. In a similar way, we are also randomly flipping the images by 20%. So that's a 20% chance that we are randomly flipping the image horizontally. So we will just flip the images over. It will be easier to see when we actually apply these transformations, how they look like. But again, this is creating random variations of the images while essentially maintaining the overall structure of the image. So then we have the color jitter, which is essentially applying a random color jitter where we change the brightness, the contrast, the saturation, and the hue. And lastly, we convert then the transformed image into a PyTorch tensor. So this transformation here will essentially, or normalization, will essentially change the pixels from the range 0 to 255, which is usually what pixel values are in an image, in a color image. It will change that automatically for us also into a 0-1 range. So in a sense, toTensor does two things. It's converting the image into a tensor, and it's also normalizing the images. However, it can be sometimes better to standardize images, as we've learned. So in addition, we also have this normalize function where we provide values for the mean and the standard deviation to normalize, or in this case, standardize the images. So we have images here with 3 color channels, red, green, and blue. And these are the mean values, so the averages. So we have the the first color channel, the second color channel, and the third color channel. So what that means is, if you recall how standardization works, we are subtracting the mean from a given pixel value. So if we have 0 and 1 ranges here, we will be subtracting 0.5 from a value that is between 0 and 1. So we will be creating, after applying this mean subtraction, we are creating then something that is between minus 0.5 and then 0.5, right? So we are subtracting this value from the pixel value 0 to 1. Then we divide by the standard deviation. So here these three values correspond to the standard deviations, again for the first, for the second, and for the third color channel. So if we focus on the first color channel again, we are then dividing by 0.5. So if we do that, we will end up with values between -1 and 1. So after applying this normalization, our images will have pixel values that are in the -1 to 1 range. And yeah, this is essentially what we do here in our transformation. Again, all of that are hyperparameters, so, or most of those, essentially those here. So again, this is something you might have to experiment with and see what works well in practice in terms of predictive performance. So one more thing to say here is that these are training dataset transformations where we have this randomness. For testing, we don't want any randomness, or when we apply, let's say, our network to new images. So for that, we have to then set up a separate pipeline for testing. So this looks essentially very similar, but there are some key differences here. So we also have two PIL image. We also have the resizing, but instead of doing a random crop, we now have a center crop here. So this is a deterministic behavior. We are not randomly cropping. We are cropping from the center to make this deterministic. And then, yeah, again, we have the same to tensor and normalize here. However, we skip those two because, yeah, this is essentially data augmentation for training. We don't want that during testing or inference or when we apply our classifier to new images. So let's now take a look at how these transformations look like. So we will start with, of course, sampling a batch from the training set. So we are going to use our Cypher10 data module. And then we are going to apply our data transformation. So let's start with a training dataset transformation here. So here we can now see the transformed training images. And if we scroll up, let's say I go up here, I make a separate window so we can see it side by side. So as we can see, the images don't look that different. So we can see this bird here is horizontally flipped compared to before. The horse is slightly center cropped. You can see the legs here in the back are missing. Or we can also see the color of this, I think it's a deer, is also different now. It's more red than brown, for example. And you can see there are these slight differences due to the data augmentation. However, we are not completely changing the training data set. These are really subtle modifications that help the algorithm to generalize better. Because with this data augmentation, we are essentially creating more training data or more variety in the training data. Now let's also take a look at the test images. So let's also do that and see if that works. So we are now using our test transforms here. And that looks pretty good to me. So here we can see there is no color jitter. So we have this deer as before. Notice that we are using still the training set images just for comparison. This is really just to compare the data transformations. So again, let's take our reference and we can see there is the center cropping. We can see the bird is slightly more center cropped. However, we don't have the color variety. We don't have the horizontal flipping and so forth. So this looks good to me. And the reason why we are doing the center cropping is that we are mimicking the kind of like zoom level that we have here in the training set. So it would, of course, also work if we don't do the center cropping. But if we apply a cropping, like here the random cropping in the images in the training set, it is also a good idea to do the same thing in the test images where we have then the same zoom level. Okay, so in this video we talked about our pipeline here, and in the next video then of course we will be using that pipeline to train a neural network and see if that can improve our generalization performance. Alright, so in this video we have seen how we can augment data using Torch Vision. So in the next video we are going to train a ResNet on augmented data and see how it performs compared to a baseline without augmented data.